this idea of there being multiple universes in space.
As this was a way in which you can explain the fine tunings.
There's a large gap at the moment between the empirical evidence and the theory.
So the idea is that every time a black hole forms, you're actually producing a new universe on the other side of the black hole.
The multiverse is a really interesting extension of what we call inflation theory. So right after the Big Bang, the majority of theories about how our universe was formed requires a very rapid period of inflation in the very, very early universe. And there are many, many different models for how this very rapid period of inflation could have occurred. But the majority of these models are called chaotic inflation theory models. And they predict that not just one universe would be created, that multiple universes would be created. And this lends itself to the idea of there being a multiverse. You can kind of, I like to imagine blowing bubbles, and there just being lots of bubbles of different shapes and different sizes around. That's kind of this idea of there being multiple universes in space. When I first started thinking about the multiverse, I really didn't like it because I thought this isn't a theory I can test because I physically can't see anything outside my own observable universe. And I think I said at the start, there's no point in coming up with a theory if you can't test it. But actually, we can test these theories of inflation. So if we can test theories, and if they make a prediction that a multiverse is the consequence of that theory, then that's a great way of actually testing this idea of there being multiple universes out there. So we can test these inflation theories. In the very early universe, when the universe experienced this period of rapid inflation, that would imprint gravitational waves. So it's an incredibly powerful event that you should still be able to see the ripples of now in gravitational waves. Now, there's been the first detection of gravitational waves recently. This is not my area of work. It's absolutely phenomenal what these scientists have managed to do. And so it's just giving them time now to improve their instrumentation, their technology, so we can get down to the sort of levels where we'll be able to see the remnants of this rapid period of inflation. And then you can really test these models. Are these chaotic inflation models the way to go? Does that really infer that there are multiple universes out there?
My final reasoning for why the multiverse is a very useful theory is the fact that you exist, that we all exist. So I've talked about these four fundamental forces in our universe. These govern everything around us, but they are surprisingly well tuned for life. So there are loads of different examples here, but I'll just take you through a couple of them. So the electromagnetic force, that's what keeps electrons and protons together. If you changed the constant that decided how well they stuck together, if you changed it by just 4%, so that's a really tiny amount, the sun would explode. No sun, no life. So just 4%, that's not, you haven't got much room for wiggle room there. What about the strong nuclear force and the weak nuclear force? If you change that just by 2%, the hydrogen would only last for about 2 minutes after the Big Bang before it got turned into helium and all sorts of other things. If you don't have lots of hydrogen created in the Big Bang, you don't create stars. If you don't create stars, you don't create life. So again, just change that number by just 2%. If you increase the mass of an electron, I think by only a few percent, DNA cannot form. If you decrease the mass of the electron, no stars can form. This is one of the smallest ones. If you increase the mass of a proton by just 0.2%, atoms cannot form. So this is known as a fine-tuning problem in physics. And scientists, we don't like fine-tuning problems. We don't like the fact that we don't understand how constants are tuned. And so the fact that we're here suggests we're in a very special universe where everything seems to be just right for stars and planets and life to form. And that would make sense. If there were multiple universes out there with lots of different realizations of physics, naturally we would be in the one that was perfectly tuned for life. But I'm sure a lot of you are more interested in the kind of the extension of that idea, the other world theory. So I've talked about there being other universes out there, that those other universes probably are not well tuned to life, that we happen to be in a really nice universe. But there is an extension to this idea of the multiverse, and that's the idea of the other world. So I'm sure you all know the idea of Schrodinger's cat. It's in a box. Is it alive? Is it dead? And the idea of quantum physics is there's no black and white. There's no right or wrong. There's a whole range of different probabilities of different outcomes. And all of these different realities are possible. It's just as likely that the cat is alive as dead. But the action of looking defines which reality that you are in. Now, the extension of this multiverse idea to this other world theory is that every time we make an action, that defines the reality that we're in. But the other action could just as likely happen, and that the universe splits in that sense. So for all of the gentlemen without beards here this evening, maybe that was a decision you took, but maybe in another reality you have very fine goatees. Who knows? But it's an interesting extension of this idea of the multiverse theory. It's, again, another thing that scientists get really anxious about. And we have, is this just going too far? Is this mathematics really pushing us into some fantasy that is no real guide of reality? And to that, I'd say the same sort of answer that I've been talking about with the multiverse. No, we cannot test this theory directly. We cannot test if every time we make a decision, you've made an alternative decision somewhere else. No, we can't test that directly. But we can test quantum theory. And quantum theory suggests that this should naturally happen. And maybe there's a nice connection between all these ideas of the multiverse and these other world scenarios.
Now, the point about the multiverse, I should make clear right at the outset, is the word multiverse is used in many different ways. There are different types of multiverse, and you need to distinguish between these before you actually start making dogmatic statements about it. The simplest type of multiverse is what Tegmark calls level one. It's simply the multiverse which says that beyond the universe we can observe, the universe began with a Big Bang 14 billion years ago. We can't see further than 14 billion light years, roughly. But there must be a universe that exists beyond that. So it's simply saying there are patches of the universe which we can't observe. And you might choose to call those other universes. I think that's pretty indisputable. But the more controversial claim is that there are also different universes which are not actually spatially connected to our universe. And the basic idea is that if you have any theory for the Big Bang, because ultimately physicists want to explain where the Big Bang came from, well, if you have a model which produces one Big Bang, obviously in principle it can produce other Big Bangs. And so cosmologists and particle physicists have come up with all sorts of ways in which they can produce many universes. You can have cyclic universes, you can have, I won't even go through them all because it would take too long to go through them all. But it's important to say that some of these suggestions come from cosmologists and some come from particle physicists. Because particle physicists also, in their own way, have produced other ideas of the multiverse. Now, the third type of multiverse is the parallel worlds of Everett, the many worlds interpretation of quantum mechanics. And again, I won't get into that. Maybe Carr will say more about that. But that's a third way. And the fourth version of the multiverse is even more controversial, which comes from Max Tegmark, who says that basically anything which can exist mathematically must exist somewhere. Now that's very controversial. I don't personally find that idea attractive. So there are these four different levels of the multiverse. The first, I would say, is pretty well inevitable. The second is really what's interesting. And the third one is to do with quantum theory, which is, no one understands quantum theory anyway. And the fourth says fantasy. So then let's really focus on the question of whether there are other universes of type 2, other Big Bangs. The first point to say is that physicists have independently come up with theories for the multiverse. That's to say, cosmologists on the one hand and particle physicists on the other. You've heard a lot about M theory, and one of the predictions of M theory is that there could be lots of vacuum states called the string landscape and things like that. So that is one reason for taking it seriously. But I also have to say that one of the reasons the multiverse became so popular was because it was realized this was a way in which you can explain the fine tunings. Because if you have all these different universes with all these different values of the constants, then it simply becomes a selection effect that we have to be in one of the universes which is conducive for life. So in some sense, the multiverse does provide a possible explanation for this mystery which was already existing. I'm saying that because I don't want to give the impression that people only thought up the multiverse in order to explain the fine tunings. There were independent reasons to believing in the multiverse. And that's why many of us at least like to connect these two ideas. But I've spoken rather long, so maybe I should let someone else carry on at this point.
I'd just like to ask a follow-up question, because some people, not necessarily me, some people claim that multiverses might be a convenient way of getting around the question of fine-tuning, simply because you could have any possible combination. Yeah. Do you have any arguments to combat that?
Yes. I mean, there are many criticisms of the multiverse, or I should say many criticizers of the multiverse. And the main criticism is simply that we have no observational evidence for these other universes. So it's fine as a speculation, but there's actually no evidence for them, because by definition we can't see something which is beyond the horizon. And therefore people say this is doomed forever to be mere philosophy. Sorry, not mere philosophy, doomed to be philosophy.
Thank you.
And that doesn't mean it's wrong, it just means it wouldn't be part of normal science. And I can only say that, of course, this argument has a lot of weight, but I can only say that I harbour the hope that there are ways eventually of getting evidence for the multiverse, and maybe we'll come on to that in the third part of the session. Until that is the case, I take the view that these ideas exist in a sort of a grey area between what I call cosmology and metacosmology. It's not proper science, but it's in a state of purgatory where it hasn't yet been promoted by evidence, because until you have actual evidence for it, it isn't proper science. So I agree with the criticisms, but nevertheless, I would take the view that any explanation is better than none, even if it's not going to be classified as science, and that's why I'm keen on the idea.
The multiverse is the idea that it might be that our universe isn't the only one, that there might be more universes beyond our own, beyond the boundaries of our own. And some people are even saying there might be an infinite number of universes beyond our own.
And why is this seen as sort of a problem, or that spans religion and science?
Yeah. So the reason is that the multiverse idea has been around for a long time. I mean, in Western philosophy, it actually has about a 2,500-year history. But it's come really resurging back in the last couple of decades, partly because physicists are looking for an answer to why the universe seems so finely tuned, why it seems like all of the constants of nature are precisely set so that the universe can emerge, can sustain life, things like that. And the danger for physics is that if you say that the universe seems really well tuned for life, that the theologians can rush in and say, aha, God did that fine tuning, right? God is a kind of cosmic mix maker who's like setting this amount of gravity and this amount of dark energy and this amount of electrons, right? And so a rival explanation to God is, no, actually, there are an infinite number of universes that take on all sorts of different configurations over infinite time. Every once in a while, one comes along that happens to work, and we seem to be in one of those universes that works.
Okay.
Yeah.
Could that argument still work with a God, though?
Absolutely. This is the thing about theology, right? It's remarkably resilient, right? A theologian can always say, right, fine, there's a multiverse, good. God created the multiverse, and then the multiverse created the universe. So it's not actually any kind of argument. The multiverse isn't any argument against the existence of God. Sometimes physicists think it is. It's not. It just sort of takes some of his jobs away, but it's not. It doesn't disprove anything. So I actually think that it's kind of uninteresting to be stuck in this back and forth over whether or not God exists, right, with respect to the multiverse. I think the more interesting question is, what kinds of new stories are we getting from these multiverse cosmologies? Like new stories about where we come from, where we're headed, what the universe is like. These are all questions that myths used to ask and answer for us in sort of any society other than our own right now. This would be the function of myths. Physics is doing it for us now. So I like to sort of look at those stories and see what kinds of values they're encoding, what they're telling us about ourselves, whether we like them or not, right? Are they telling us good, helpful things? Yeah.
So what are some of these new stories that they're telling us?
Right. So, I mean, there are tons of them. If you ask, most theoretical physicists, they'll say, right, well, there's only one respectable one. The respectable one is that there's this sort of primordial sea of inflationary energy. Inflationary energy sort of pushes space out really, really super fast. And this primordial sea races and races and races outward. And every once in a while, that energy kind of turns off and allows little pockets of stable space-time to form. And those are universes. So you get these universes nucleating out of this sort of primordial sea, like sort of pockets of air in Swiss cheese or something like that. So universe, 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 universe. This is called eternal inflation. And the idea is that our universe is one of just these bubbles in this eternal sea of inflating sort of hyper space-time. That's one of them. There are other theories that argue that every time a massive, massive star collapses and forms a black hole, you get, so that you've probably seen drawings, right, of space-time kind of going like this, you get an infinite amount of stuff in zero space. You have stuff crammed into no space. So you've got a sort of point of infinite density. That point is called a singularity. Physicists also talk about singularities or the singularity as having been what the Big Bang was, right? A bunch of stuff crammed into a point of no size. So the idea is that every time a black hole forms, you're actually producing a new universe on the other side of the black hole. So we may have, right, hundreds of millions of black holes in our sort of visible universe, and each of them, the idea is, would have potentially a universe inside it, and conversely, we're sitting on the inside of somebody else's black hole, right, in that universe. That's another idea. An idea that people love to ridicule is the idea that our universe is all sitting on a 3+1 dimensional membrane, and that membrane has like a partner universe, which is also a 3+1, 3+1, 3 of space, 1 of time dimension, and they're sort of hovering near each other, separated by this fourth dimension of space that nobody can see, but it's like right there. So this other universe would be like right here, just closer than anything to us, but we just can't cross the gap to that other universe. That every like couple trillion years or so, these two membranes smash together. That's the Big Bang. The universe is destroyed, recreated all the time, and we've got this kind of symbol crashing that makes and unmakes the universe. These are some ideas, right? I find this fascinating, right? Why not look at these new stories and ask what it is they're telling us?
But that, to me, gets to the question. The difference between something that is compatible with a mathematical description or a mathematical theory, or compatible with a logical description or logical theory, and something that actually is, in fact, the case, right? So when I hear things like, for instance, string theory predicts a certain number, a different number of universes, well, not really, right? What it does, it's compatible, it's mathematics, is compatible with the existence of a large number of differently arranged universes. That's not the same as making a prediction. Because in order to make a prediction, you have to somehow bridge the gap between the mathematical theory and the empirical evidence. And that's where your discomfort, shall we say, with the multiverse, I think, is justified, right? Because there is the question, the fundamental issue in science is everything stops at the buck of the empirical evidence. If there is no empirical evidence, it's not science. End of story. Even though not a lot, a good number of physicists these days are beginning to talk about something that worries me particularly, which is called post-empirical science. Okay, post-empirical science is something that to me sounds a lot like metaphysics. And I don't have a problem with metaphysics, but the physicists usually do have a problem with metaphysics, right? So what I think might be helpful here, and you were actually going in that direction already quite a bit, is to make a distinction. There are no sharp distinctions between physics and metaphysics, I think, or between physics, science and philosophy necessarily. But there are distinctions that I think need to be made. And one of the problems why I think so many philosophers and so many physicists are uncomfortable with both string theory and the multiverse is precisely because, especially when it comes down to books published for the general public, that distinction is completely blurred. If you read The Elegant Universe by Brian Greene, I did, and when I read it, I got the impression that, oh, this is physics. This is, the physicists have, in fact, basically settled this issue or close to settle this issue. Nowhere near. And the reason it's nowhere near it is precisely because there is a large gap at the moment between the empirical evidence and the theory.
For more debates, talks, and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.